All right, 2.4, we're going to talk about limits. Finally, right? Some new material. Maybe you were kind of basking in all the excitement of algebra, but now we get to talk about calculus today. All right, so today we're going to evaluate limits approaching a constant graphically, numerically, and algebraically. So we're going to have a couple different ways that we're going to evaluate limits. And we're going to evaluate limits approaching plus or minus infinity, graphically, numerically, and algebraically. So there's a lot to do here in this section. All right, first things first, the limit question. Here's your notation, and it's the limit as x approaches c of f of x. So sometimes when we see this notation, students don't know what to say. So they're like limit f of as x arrow c, and they don't know how to say it. So let's write this out in English so you know how to properly speak about limits. The limit of f of x as x approaches c. That's what that means. So we're going to be using this notation. It's LIM for limit, and then you're going to have a value to which x is heading, and then we're looking at functions of x. So the question we're really asking when we talk about a limit, because I know right now we're just like, okay, but what is a limit? Well, what we're trying to figure out is what real number do the y's approach as the x's approach c from both sides. Now we're going to focus a little bit more in the next section about really looking at one-sided limits. I know that means nothing to you right now, but watch as I sort of approach here from both sides. So notice that we've got these x values down here on the x-axis, and then of course you've got your y-axis. You've got some x value c, and then you've got this corresponding function value f of c. So what's happening here is as your graph, which is this curve, approaches, as the x values on your curve approach c, as we head maybe down from the right, you're noticing that the value of y is approaching f of c. So that's the whole idea here. It's just what y value are we approaching as x approaches c from either side. So now as I approach c from the left, I can say the same thing. So x is approaching c now from the left. I know we always think about x values as moving horizontally, but we're moving on this curve here. So you can kind of follow the arrows this way. And as we approach c from the left, again, we're still approaching the same y value, and this y value is the one in the box. Now, what you can see over here to the right is sort of just like a zoomed in picture of what's really happening as you approach c from both sides. So as x approaches c from the left and from the right, the y values sort of narrow in on this value. So if we're thinking about x approaching c like this, the y values approach f of c as they move in vertically. Kind of a breakdown of the way that would look. You're going to see a bunch of examples of this, though. So this is sort of just a general vague picture of what could be happening in a limit. So we're not necessarily talking about the function value. Sometimes we will be, but sometimes the limit has nothing to do with the function value at a point. First, we're going to talk about looking at a graph, very similar to what we just did, to talk about values of a limit and how that maybe differs from the value of the function. So I have this graph here to the right that we're going to be referring to. It says determine the following using the given graph of the function f of x. I know it's a little bit blurry for you to see because I don't want to zoom in too much. It's a pain to zoom in and out, but you have your notes in front of you. Should be good. So that's y equals f of x. So the first thing we're going to find is f of 3. So remember we talked last week about looking at function values, and we said that this just means what is the value of y when x is equal to 3. So as I'm looking at my x-axis and I'm looking at x equals 3, well, the value of y would be right here. So this value corresponds when x equals 3 to about y equals 1. And I know it's not necessarily labeled, but you can probably label it pretty comfortably as being the 0.31. So when x equals 3, we would say that no problem, we can tell that the y value on the graph appears to be 1. Now, when we're asking a different question, which would be, what is the limit of the function as x approaches 3? We're not necessarily asking for what the value of y is. We're looking at what value y approaches as x approaches 3 from both sides. So what we're doing here is saying, all right, well, if I'm going to approach 3, let's say maybe from the left, we'll start from the left. Maybe I'm sitting here at 2 on the curve, and I'm going to approach 3. So if I'm on the curve and I'm looking at x values that are 2, the y values are up here now, we'd be heading down and down and down and down. And then eventually, as x gets closer and closer and closer to 3, y would get closer and closer and closer to 1. Now, notice that if you repeat that same process on the right-hand side, if we approach x equals 3 from the right, you'll see that same type of behavior. So approaching maybe from values that are closer to 4 and then moving in towards 3 from the right, you'll see that the function values head down until you get approximately to this value y equals 1. And on both sides, you can see that the function value is approaching y equals 1 as x approaches 3. So that's the deal with the limit. Now, if you still can't tell the difference between parts A and B, you're going to see a difference illustrated in some of these other examples. So this was just an example where it happens to be the case that the function value is the same as the limit, but that's not always going to be true. Let's look at a couple different examples. For instance, f of 4, that's saying what's the y value when x equals 4? Well, when x equals 4, we're right here. I can move this up and I can see that it approximately gets me to this open circle on the graph. Now, remember, when there's an open circle on the graph, it means that your value of y doesn't actually exist for that function value. So if I was saying, or if I was asking you, what is the value of y when x equals 4, you'd be like, there's an open circle there. There's a hole. Yeah, y doesn't exist when x equals 4. So that's all you can say for the function value, is that f of 4 does not exist. Now, a lot of times we're going to be using this notation a lot when we say does not exist. Of course, you can just write does not exist, or you can say it's undefined, but DNE usually is just shorthand for does not exist. Okay. So the function value at 4 doesn't exist. Let's look at what happens with the limit at 4. Like, does that exist? So just because the function value does not exist doesn't mean we can make a conclusion about the limit. Let's approach 4 from the left and from the right. So as x goes from 3 to 4, it's moving its way along this curve now in the opposite direction. I'm actually still approaching a particular value. I'm approaching y equals 2. Now, it doesn't matter that there's an open circle at the point 4, 2. What does matter is that the values of y are getting really, really close to y equals 2. Now, they're not going to get there, but they might get to like 1.9, 1.99, 1.999. They're going up, 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 up. It's just that when we appear to get to this maximum value at 2, we have this open circle. So the function can't exist, but we can get close to a value. We can approach a value. And we can do the same thing on the right. So as x approaches 4 from the right, again, we're just going to follow the values along this curve and look and see, like, does y approach a value? And it does. Y is approaching 2. Now, it's never going to actually get there, but it doesn't matter. The limit is just about what value are we approaching. And it must be the case that we're approaching the same value from both sides. So you can see that from the left and from the right, as x is approaching 4, the value that y is approaching is 2. Therefore, the limit of the function is 2. So it might be the case that the limit exists even if the function value does not. So that's the big difference between actually being able to find a function value and talking about the limit of a function at a given value of x. All right, let's see. Let's do this for another point, f of 1. So we're looking at what happens when x equals 1. That would occur right here. Now notice that as you move your way up vertically, there's an open circle at 1, 1. So that means the function's not actually defined as y equals 1 when x equals 1. But if you look up a little bit further, you'll notice that y is actually defined at x equals 1, but the y value is not 1, it's 2. So this happens. I know it's a wonky, strange graph, but it's the kind of graph that teaches you how to find limits. That's what I love about these weird graphs. It really kind of tests your knowledge of, do you know what a limit is? So the function value at 1 is actually 2, because that's where you have the filled in circle. The open circle isn't telling you anything here about the value of the function. Now, regarding the limit at 1, we have a little bit of a different situation, because remember, the limit as x approaches 1 isn't asking you what's the y value at 1. It's saying what value does y approach as x approaches 1. So as x approaches 1 from the left, you're following this curve along. And as we approach 1, the y values also approach 1. And we can do the same thing from the right. As x approaches 1 from the right, the y values also approach 1. Doesn't matter that the function is defined at y equals 2. It doesn't matter. The value that y approaches as x approaches 1 on both sides is actually 1. So this is a case where the value of the limit doesn't equal the value of the function at a given value for x. Really interesting, right? You know, these are really very specific instances, but make sure you understand the difference between finding a function value and finding the value of a limit. This is crucial. This one example is just so important. F of 2. So this is saying, all right, x is equal to 2. What's the function value? Well, the function value at 2 is 2. So we have the filled in circle. The curve is leading us there. If you're wondering, well, what's going on with this? It's an open circle, so we don't have to worry about it. As far as the function is concerned, f of 2 is 2. Now, the limit is where we're going to have to put a little bit more thought into what's going on with this situation with the open circle. So now we're talking about the limit as x approaches 2. Well, as x approaches 2 from the left, you'll notice that y approaches 2. So I'm approaching this value where we have this open circle, this closed circle. Sorry, I'm like running out of space to put my little arrows here. They start to look like little caterpillars. As I approach x equals 2 from the right, however, I'm talking about this leg of the graph that approaches from the right. And the values that y will approach will be values that are approaching 3. So I'm getting here, even though I can't actually attain 3, I'm actually, as x approaches 2 from the right, I'm getting to values maybe like 2.9, 2.99, 2.999. And I can get infinitesimally close to that value, but I'm not going to reach it. Either way, I've got a big gap here, and the y values are not approaching the same value. As x approaches 2 from the left, our function's approaching 2, but as I approach from the right, the y values are approaching 3. So in this case, we would say that the limit does not exist. And this is because the values that y approaches on the left do not equal the values that y approaches on the right. We're going to, again, talk about that more when we look at one-sided limits in the next lesson. Because the y values are not, I'm going to say, approaching the same value as x approaches 2 from the left and the right. So as we approach 2 from the left, the y values were approaching 2. And as we approach from the right, the y values were approaching 3. We should say y goes to 3. It's not actually going to reach that value. So that's why we have the limit does not exist here for that particular reason. All right, the last thing we're going to do on this page is something that is kind of a rite of passage for all calculus students. Now you get to do it. We're going to evaluate limits numerically, and we're going to do this using our calculators. So I'm going to show you how to do this in your table. Let's see. Let me get my brightness fixed here for you all in the daytime. There we go. I know sometimes I sit here at night, sometimes I sit here during the day, and every time I have to adjust the brightness on my calculator because it has a mind of its own. I'm going to take this function and I'm going to plug it into my y equals. Now, when you put a rational expression into your graphing calculator, make sure that you put parentheses around the entire numerator and the entire denominator. So we have x squared minus 4 divided by parentheses x minus 2. So my numerator's in parentheses, the denominator's in parentheses. Now, I'm going to be looking at specific values of x here and talking about what values y will approach as x approaches 2. Now, notice in your table here, we're going to approach 2 from the left, so from values that are less than 2, and then from the right using values that are greater than 2. So what I'm really going to be focusing on is what actually happens at 2. So think about this in terms of a number line. You're getting to be larger up to 2 and then going past 2, but getting super close to 2 and then sort of moving away. Now, I'm going to look at these particular x values. You don't have to actually plug all these into your calculator individually. The way that we usually do this is just by using our calculator table feature. Now, I pretty much always have my table set so that my independent variable is, I have to enter it myself. Let me see, what do they call that? Not automatic, ask, that's what they call it, ask. So sorry, how I got to that was I hit second and window, and that brings me to the table setup. Now, if you have your table set right now to auto, what you're going to see is that your table automatically just generates a bunch of x values for you. Usually, if you haven't changed your settings, it'll go like 0, 1, 2, 3, 4, 5. Well, we don't want 0, 1, 2, 3, 4, 5. So like, for instance, if you're in auto right now and you go to your table, it's just going to give you x values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, I want 1.9, 1.99, 1.999. That's why I'm going into my table set, and I'm going to set my independent variable to ask, not the dependent. Remember, your independent is x, and that's what you want to change. Your dependent is always going to stay in auto. And then we'll go to our table itself. So second graph, and it's going to give you a blank table now if you've just set this way. Sorry, I'm going to have to redo my focus to focus on the calculator, but maybe if I put it in the middle somewhere. So the x values I want to look at are 1.9 and 1.99 and 1.999. So these are the three that are on the left. Now, when you enter these in your calculator, you're going to get some y values on that function. I'm going to go ahead and just put these y values down first, since these were the ones I had on the left. So when I entered x equals 1.9, I got 3.9. And then at 1.99, I got 3.99. And at 1.999, I got 3.999. Now, I always have students who are like, wait, I got different numbers than you. Pretty much every single time that happens, I have them check their function to make sure they put parentheses around the numerator and denominator separately. If you mess up your parentheses, you will get different numbers in your table. This always happens all the time. Make sure you've entered your function appropriately. I'm going to go back to my table now, and I'm going to look at the values 2.01, 2.01, 001, 2.01, and 2.1. I think I missed a 0 there when I was saying it. And 2.1. So now I get these values that are 4.001, 4.01, and 4.1. Now, notice, by the way, I didn't mention this at first, but this is kind of important. If I was to actually think about the function value, f of 2, I would have a problem. Because if I'm looking at f of 2, I've got 2 squared, which is 4, minus 4 is 0, divided by 2 minus 2 is 0. 0 over 0, by the way, is not 0. But we would have a hard time finding that function value, but we can find the value of the limit. We just looked at the values of y as x was approaching 2 from the left and from the right. And what we ended up getting there was that as we approach from the left, our values were getting really super close to 4. And from the right, our values are also getting super close to 4. Now, in this case, you're going to estimate the value of the limit. You're looking for these values to start to converge upon a number. You're wanting them to agree, and they do. From looking at this table, you can clearly see that the values that y is approaching as x approaches 2 from both sides is 4. So you're going to make that guess. I mean, it's not much of a guess. It's pretty obvious, but, and you're going to say now that the limit is 4. So the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. Remember we talked about how we were going to look at these in a bunch of different ways. If you wanted, it'd probably be a good idea, since you already have this function in your graphing calculator, to look at this and just see it visually on the graph, that the limit is 4, meaning the y values approach 4 as x approaches 2, because we were having a hard time being able to evaluate the function. Let's go ahead and look at the graph. I just hit the graph button since my function was already in there. And this is going to look odd to you because you're like, huh, this looks like a line. I was expecting a little bit more. Well, we'll get into why that's the case. It's something you should have talked about in algebra. You can always factor and cancel here, and you would end up with x plus 2, which is this line. And you can see now that as x approaches 2 from the left and from the right, that the y value approaches 4. So it makes sense on the graph, kind of taking this back to what we did in that first example. So expect to see something like this on your test and expect to see something like this. Both of these things are incredibly important. Being able to look at a graph and tell me about a limit, and being able to find a limit numerically. So usually when we say find a limit numerically, that means complete a table. If I put this on an exam, I'm probably going to put the table down for you, just because I don't want anybody guessing about what numbers to use. But always use values that get super close to your number. Like if I'm looking at what happens as x approaches 2 from the left, I'm not going to say 1.1, 1.3, 1.4. Those numbers aren't that close to 2. I want to start out close, and then I want to get even closer. All right, now we're bringing this back to the piecewise function, which we graphed one of these a couple lessons ago, but we'll do that now. I know, I love piecewise functions. I don't know, they're just cool. All right, we are looking at the limit as x approaches 1 of f of x, and we're first going to graph the function. So basically, we're going to take this and turn it into a graph similar to what you just saw on the previous page, and we're going to evaluate the limit using the graph, and then we can, of course, look at these values algebraically as well. So without further ado, notice that your boundary point is x equals 1. That's where all of your graphs are changing. So if you would like to make a dashed line at 1, just so you know where your cutoff is, you can. It's not like an asymptote or anything, but like I said, I just like to have this on here just so I remember that I do have this boundary. So this is x equals 1, and that's where my function is going to cut off and switch to another one. Now, if I were you, I would do the easiest thing first. That is the middle definition. F of x, which means y, equals 4 when x equals 1. That's just a point. So if x equals 1, y equals 4, fill that in with a point. It's just a closed circle at the point 1, 4. Now, as far as graphing the other two lines, you could, like I said, graph both and then erase the parts that you don't need, or you can just plot some points to make some nice smooth lines and curves here. I'm going to start with this first definition. So we're going to choose some values of x. And remember that even though technically x equals 1 is not on this graph, we're going to look at what happens at 1 anyway, just so that we can see what happens as we approach that boundary. And their function value is negative 2x plus 4. So when x equals 1, I'm going to look at that value, but I'm also going to be looking at values of x that are less than 1 on this definition. So, I mean, it's linear, so you don't have to be too crazy about which values you pick. And because it's linear, I know I really only need 2 points to graph a line, but I'm going to get these 3 points. Now, because this doesn't actually exist, 1 on our graph, we're going to put an open circle on this point, whatever it ends up being. Open circle. Because it doesn't really belong there, but it's going to guide our graph. So we've got negative 2 times 1 plus 4, which is going to be positive 2. So we're going to have an open circle at 1, positive 2. If you want to go ahead and plot that now, you can. And remember, if you accidentally graphed a point there, you might start to think like, wait a second, this wouldn't pass the vertical line test. It can't be a function. And then hopefully you'd be like, yeah, I need to go back and fix that. So if you've already got a closed circle, there's no way you can have another closed circle vertically underneath or above it. Otherwise, you don't have a function. When x equals 0, you have negative 2 times 0 plus 4, which is 4. And for negative 1, we'll have negative 2 times negative 1 plus 4. Well, that's positive 2 plus 4 is 6. So I've got a point at 0, 4, and I can fill that in because that actually exists here. And then I've got another point at negative 1, 6. And we know that the slope of this line is negative 2, so we're going down to right 1 for this slope. And you can just connect these with a nice straight line. And this is y equals negative 2x plus 4. And notice that if we hadn't graphed this open circle, we'd have a big gap here. That's why I just like to graph it, but make sure it's just open wherever that boundary is. Now we'll graph the other portion of this. So I've got x equals, we're going to figure out some values. Again, I'm going to figure out what's happening at the boundary itself. And then the y value is x squared plus 1. Now, we did one of these with the square root where we really had to really focus on choosing the correct values of x that would give us nice integers to work with. But when we're squaring values, mostly we just want to make sure they don't get too large really quickly. So don't pick anything like 10 because 10 squared is 100 and we don't want to have to graph 101. So that would be way out here. We don't want to have to deal with that. So maybe we'll choose 1 and 2 and then 3 we should be able to fit because 3 squared plus 1 is 10. So we can fit that one for sure. All right. So remember, if you're remembering your college algebra, this is just your standard parabola shifted up 1 unit. So if that helps and you just want to graph the parabola and erase the portions you don't need, that's okay too. So this will be 1 squared plus 1, which is 2. This is where we're going to have an open circle. We're going to have that in both places where we have x equals 1. Now, interestingly enough, it's the same open circle at 1, 2, and 1, 2 for both of these graphs. It's already there. All right. Well, interesting because we're talking about limits. We'll see what happens with that. When x equals 2, we have 2 squared plus 1, which is 5. And when x equals 3, we'll have 3 squared plus 1, which is 10. So I'm going to have a point at 2, 5, and 3, 10. So 2, 5, and 3, 10. So it's got this shape of a parabola that's shifted up 1 unit. Try to make it look curved. I know like once we get beyond the vertex of the parabola, it's kind of hard to make it look curved. But again, that's partially why we go up to the boundary point. So we don't just have this gap here and it just ends up looking like a straight line. So your graph actually looks like this. Now, the question is, I know we already graphed the piecewise function. You're like, okay, next. But we actually had to answer a question here about a limit. So we're looking for the limit as x approaches 1 of f of x. So this is your function f of x. Here's the corresponding graph. The question is, what's the limit as x approaches 1? What are the y values approaching as x approaches 1 from both sides? Well, in this case, notice that even though f of 4 is 1, or I'm sorry, f of 1 is 4. I said that backwards. F of 1 is 4. It doesn't matter. The function value and the limit value are not going to be the same here. as x approaches 1 from the left, you're going to see that y approaches 2. And as x approaches 1 from the right, again, y approaches 2. So we would say in this case that the limit as x approaches 1 of f of x is actually 2. Where am I going to put this? The limit. So we're going to say the limit as x approaches 1 of f of x equals 2. That is the value that the y's are approaching as x approaches 1 on both sides. So not equal to the function value, but that's fine. It doesn't have to be. That's how we would do this. Again, with just another example using this graphically. We already talked about a graph on the previous page. To evaluate a limit, we're going to talk now about evaluating limits approaching a constant algebraically. This is kind of a nice thing to do. To evaluate the limit as x approaches c of f of x, first try direct substitution. In other words, f of c. Anywhere you see x, you're going to swap it out with c. So we're going to plug in c for x. Or officially, we're going to evaluate f at c. But you like to say plug in c for x, so fine by me. If f is continuous, because this is not going to work all the time, but we can do this if f is continuous at c. If that's the case, then the limit as x approaches c of f of x will be f of c. Now, we haven't talked a lot about what it means to be continuous, but I'm going to give you a couple of things here to watch out for in a second. If f is not continuous at c, then direct substitution will not work. And you're going to have to use a different method then. Maybe the numerical method where we had the table of values, or maybe a graphical method. So in particular, we're going to watch out for zeros in the denominator, that's one big thing that's going to cause the function to be not continuous, or cutoff points of piecewise functions. I was calling them boundary points, but so maybe I'll just call them boundary points. Or cutoffs of piecewise functions. So that function that we did above in example 6. Oh, for some reason I thought I had my example numbers all messed up, but no, it was example 6. That was a piecewise function. So we had to look at that situation where we had something funny going on. That will be a case where you can't try direct substitution. If you were to have tried direct substitution there, the function's not actually continuous at that point, so you wouldn't have gotten it to work for you. A function is continuous if you can graph it without ever having to lift your pencil. This function is not continuous at x equals 1. It's continuous everywhere else. Here you just have a linear equation. To the right, you have a quadratic. The problem occurs at the boundary. At the boundary, you have this situation where all of a sudden you have this hole in the graph and you can't graph it anymore without having to actually lift up your pencil. Now, if you redefined the function and let's say we said that f was 2 when x equals 1, well, you'd have a continuous function, but we didn't have that in that case. So we need to watch out for situations like that. So that's what this number 2 down here is all about. Now, these do not mean the limit does not exist. So these do not mean the limit does not exist. I mean, it's possible, but that's not a given. It just means you're going to have to find another method of figuring out the limit if you can't use direct substitution. So this is just a method that we're going to use to evaluate limits algebraically. Example 1 of evaluating limits algebraically. This is the way you're always going to do it, by the way, if you can, if you don't have an issue with continuity. We're going to look at the limit as x approaches 3 of 2x minus 1 over x plus 4. Now, you'll know that you won't be able to do this if you go to plug in c for x and you end up getting a 0 in the denominator, or if you originally had a piecewise function, you would know already that you would have an issue there with direct substitution. But this is not a piecewise function, so we only need to worry about what happens if we have zeros in the denominator. But in this case, I can just say that 2 times 3 minus 1, again, just everywhere I see x, I'm substituting in the value of c, which in our case is 3, and then divided by 3 plus 4. 2 times 3 is 6, minus 1 is 5, and then 3 plus 4 is 7, and the limit is 5/7. Now, there are so many different ways you can look at this. I don't want you to feel like you have to do limits one way or another. We could look at this function graphically. If I put this into my calculator as 2x minus 1, oh no, 2x, if I just would have rewritten the function, it probably would have been easier. Divided by x plus 4, I can take this same exact function, put it into my graphing calculator, and I can look at the graph, and I can verify that the limit is 5/7 is a little bit less than 1, but we can eyeball that and see if that makes sense. That as x approaches 3, 1, 2, 3, that the y value is a little bit less than 1. And that does indeed appear to be the case. You could always check that too in the table. Because we did direct substitution, that's basically just like looking at the table. So I can look at what happens when x equals 3 and notice that I get a value that is, you can hover over it and get a longer decimal, by the way, 0.714285. Well, that is the same decimal value as 5/7. So this is a great example of how you can evaluate a limit 3 different ways. You could even go to the table and verify that it's approaching that value, but you don't need to because we can evaluate the limit directly. So we just looked at it numerically, we looked at it graphically, and we looked at it algebraically. Come on, it doesn't get any better than that, you guys. Awesome. All right, let's do another one. Of course. Let's see. So I'm still trying to figure out this situation with my camera. Got it. So the next one will be a piecewise function. This is going to be g of x equals, the first definition is going to be x minus 2. The second definition is negative 2x plus 8. Now, for the first definition, that's going to be true if x is less than or equal to 3. And for the second definition, this will be true if x is greater than 3. Now, what we're going to do is we're going to take this function and we're going to find the limit as x approaches 4 of g of x. Now, if you're kind of thinking like, oh my gosh, she just gave me a piecewise function. This is torture. I hate this. Don't worry about it because this is not a boundary value. C in this case is not a cutoff. So all you need to do is use direct substitution and figure out which one of these definitions is going to match your situation. So as x approaches 4, that means you're looking at values that approach 4 on both sides. So you're looking at like 3.9, 3.99. All of those values are going to be values that are greater than 3. And then, of course, 4.001, 4.01. All of that will follow this definition. This is where x equals 4. Not here. The first definition is for values of x that are less than or equal to 3. But our value is 4, So we're going to use the second definition with direct substitution. So now we can say that our limit is equal to -2 times 4 plus 8. We can use direct substitution because we're not sitting on a cutoff point or a boundary point, and we don't have any denominators where we could possibly have 0. So direct substitution works. I have -8 plus 8, which is 0. And that's okay. 0 is just fine. It's a number. It just means that the y's are approaching 0 as the x's are approaching 4. That's it. And remember, we can do that because 4 is not a boundary or cutoff point. All right, so now let's talk about what would happen if you did have that, oh my gosh, worst case scenario, she gave us a piecewise function and we have to evaluate the limit at the boundary. It's fine. You've done it before. We'll do it again. This time we're just going to talk about using direct substitution instead of looking at it graphically. So that's the nice thing here is like, I'm not going to make you graph the next one. No, we're going to do this algebraically. So remember, cutoff point, we've been calling boundary, but they're the same. You call it whatever you want. So we're going to talk about evaluating a limit as x approaches c of f of x, where c is some sort of cutoff or boundary point of a piecewise defined function. So two things here. The first is the limit as x approaches c from the left. We're going to add some new notation for that next time. The second is the limit as x approaches c from the right. These two have to be equal in order for that number to be the limit. So we would say that if you take the limit as x approaches c from the left, and then you take the limit as x approaches c from the right, if these numbers are equal, then that number is the limit. Otherwise, the limit does not exist. Now, think back to that cool graph that we did here. If we were to evaluate each of these functions at 1, and we did that, we ended up getting the same y value, which was 2. Therefore, the limit was 2 because those numbers were equal. We're going to do that this time without graphing. So your example 3, I'm going to give you the same definition for g that we had in example 2. It's x minus 2 and -2x plus 8 if x is less than or equal to 3 and if x is greater than 3. This time I'm going to ask you about the limit at the boundary. Oh, and if you're trying to gauge how much space you need, this is the last one we have on this page. Okay, so the limit as x approaches 3 of g of x is what we are going to find. So I'm going to look at the limits on the left and on the right. So from the left, I'm looking at values that are less than or equal to 3. So I'm going to use that first definition. So on the left, we know that x is less than or equal to 3. And we could say that f of 3. Oh, you know what? I keep calling it f, but this function's actually g. G of 3 is following this function now, and we have 3 minus 2, which is 1. Now we're going to look at this from the right. Now remember, we're not talking about the actual function value. If we were looking at the actual function value at 3, then we would just find g of 3, which we just did. but we're looking at the values of the limits, which means the values that y is approaching as x approaches 3. So when I actually do this from the right, now I'm going to use this definition. And I know that seems odd because you're like, wait, but 3 is not greater than 3. Doesn't matter. We're not talking about the function value. We're talking about the value of the limit. So we're looking at what y values g is going to approach as x approaches 3 from the right. And we're going to look now at g of 3 from the right. So this will be -2 times 3 plus 8, which is -6 plus 8, which is +2. So if you were to graph this, that open circle that you would have would be at 2. So we could say now that the graph would have an open circle. Graph of g would have an open circle at 3, 2. Sorry, got an extra parenthesis in there somehow. So the graph would have an open circle at 3, 2. Therefore, we would say that there's no way, well, that really doesn't have anything to do with the limit. What really makes a difference here is that 1 does not equal to 2. Because 1 doesn't equal 2, we would say that the limit does not exist. Remember, what we're looking for here is that if we take the limit from the left and the limit from the right, if the numbers are equal, then that number is the limit. Otherwise, the limit does not exist. And that's what we've got. We've got a limit does not exist situation. Okay. Okay. Let's look at some other situations. We talked about cutoffs for rational functions where we might have zeros. We talked about cutoffs for not rational functions. They could be rational, I guess, for piecewise functions. Now we're going to focus a little bit on rational functions. So here I'm going to give you the limit as x approaches -2 of x squared minus x minus 6 over x squared minus 3x. So what we're looking for here when we use direct substitution is, are we going to end up in a situation where we have 0 in the denominator? Because if we do, then we can't use direct substitution. But we're going to work our way through this and see what happens. Notice that -2 squared is +4, and then -3 times -2 would be +6. So we're not going to end up here with 0 in the denominator. But we can go ahead and everywhere we see x, we can swap it out with -2. Be careful with your negative signs here. And you have this situation. In the numerator, we'll have 4 plus 2 is 6, minus 6 is 0. Now, don't panic because 0 in the numerator is not a bad thing. It's 0 in the denominator that we don't like. -2 squared is 4. Plus 6 is 10. 0 divided by a real number is just 0. That just means your limit is 0. No big deal. The y's approach 0 as x approaches -2. So we've got that. Let's talk about, though, a different situation that might occur with the same function. And I'll just remind you, 0 divided by a number that's not 0 is 0. I know, such scientific definitions I'm giving you here today. Number, oh, you know what? I have messed up my numbering so many times. I just want to verify that my number is matching yours. Yes, 5. I don't know. Okay, let's talk about what happens when we end up getting 0 over 0, because this happens quite a bit in calculus on purpose, but this is called an indeterminate form. It's not 0. 0 over 0 is not 0, and it's not undefined. So maybe we should say that. Undefined is a different situation. And you know what drives me crazy is when a student gets 0 over 0 and they say 0 over 0 equals 0. Done. No, you're not. 0 over 0 is not 0, and it's not undefined. So don't say that either. Indeterminate means like we need more information. We don't have enough information. If you get 0 over 0, this is an indeterminate form. So you're going to try an algebra trick like factoring and reducing. That's the best kind. Factoring and reducing. Or rationalizing the numerator or denominator and reducing. I know that sounds awful to you, but it's not that bad. Rationalizing the numerator or denominator, then reducing, and then reevaluate the limit. So I'm going to give you an example of each of these, which are rites of passage for any calculus student. You're not the first people who've ever done problems like this. It happens constantly all the time. These are very, very standard calculus examples for evaluating limits. So here's the first one. It's going to look kind of familiar, but not exactly the same as one you've looked at before. X squared minus x minus 6. Yes, it should look familiar to you because you saw this function back up here in example 4. Now, I'm going to try to smash 2 examples in this space if you're trying to space things out. I should have moved this box up a little bit, but that didn't happen. So try to use your space wisely. If you were to use direct substitution here, notice that in the denominator, check the denominator first, you'd get 3 squared minus 3 times 3, which is 0. And then you're thinking like, okay, well, that's not the end of the world. Maybe I'll just get a number in the numerator and it would be undefined. Well, oh, we should, you know what? We should have written that up here. I said 0 divided by a number, which is not 0. Oh, you know what? We're going to talk about that in another box. Sorry, I'm off on a tangent here. Let's go ahead and evaluate the numerator. 9 minus 3 is negative 12, 9 minus 3, not negative 9. 9 minus 3 is 6, minus 6 is 0. Don't panic, it's indeterminate, but that's okay because you know what to do. We're going to rewrite this using algebra. Don't rationalize because we don't have, this would be the situation where you have like a radical. We don't have that. We're going to rewrite this polynomial in factored form. So I'm going to take my polynomial and I'm going to rewrite this as the limit as x approaches 3 of, and when I factor this, the 2 numbers that multiply to negative 6 and add to negative 1 are going to be negative 3 and positive 2. So I'm going to rewrite this as x minus 3 times x plus 2. And then in the denominator, I'm going to factor this just by taking out that GCF of x. So the whole idea here is that when I factor this, I can cancel out a factor, and usually that's what's causing an indeterminate form. Now, when you cancel that out, you can rewrite the limit one more time. The limit as x approaches 3, but now I'm rewriting the function as x plus 2 over x. Now you're not going to get an indeterminate form again. This just becomes 3 plus 2 over 3, which is 5/3. And again, though, this is something that you could check in your calculator. Even though it's indeterminate, you could still put this function into your graphing calculator and start to approach 3 using incremental values like 2.9, 2.99, 2.999, and then head back the other direction. And you would be able to, you might not be able to narrow in on 5/3, but if you had an idea that it was 5/3, you could certainly check it that way. But you wouldn't be able to evaluate this function there. You would have to evaluate that function using direct substitution because this one doesn't have 0 in the denominator. So let's do an example of the rationalizing. You won't see a ton of these, but it is something that a lot of calculus students see. It's a very standard type of example, so I wanted to make sure to show it to you. The example is the limit as x approaches 9. of the square root of x minus 3 divided by x minus 9. Now, if you went to evaluate this using direct substitution, you would notice that you get 0 over 0, which is indeterminate. So what you're going to do is you're going to multiply by the conjugate. That's the most straightforward standard way of doing this. If you don't remember the conjugate, you learned it back in college algebra when you were talking about complex numbers. You learned about conjugates. But we're going to do the same thing here for our radicals. So I'm going to rewrite this function. I'm going to take it out of the limit for a minute so I can work on it. So this is going to be the square root of x minus 3 over x minus 9. Now, if you don't remember what the conjugate is, you use this for complex numbers, so it would make sense that you're going to use this for radicals. They're very closely related. It's when you take the same expression, but you change the sign in between the terms. You don't multiply it by a negative, you just change the sign in between the terms. So the idea is if I take this expression and I multiply it by the square root of x plus 3, I don't want to change the expression, so I need to multiply it by a special name for 1. So I'm going to change this to be the square root of x plus 3 times the square root of x minus 3 in the numerator, and then we'll multiply in the denominator. Now, we're going to put this back in the limit in a minute. Right now, I just want to simplify this expression. So this is the conjugate. So here, the trick is that we multiply by the conjugate from algebra. So just change the sign in that radical expression in between the terms. Now, when I do that, x times x, we're going to FOIL here. First terms are x times the square root of x times itself, which is just x. The outside and inside terms are going to be additive inverses. They're going to go away. That's the whole point of the conjugate. So you'll have 3 root x minus 3 root x. The whole point of the conjugate is to get rid of those outside and inside terms. Now, the last terms give you minus 9. Don't also FOIL in the denominator in this case. And by the way, you might have to multiply by the conjugate of the denominator instead of the numerator in some cases. It just depends on where that radical is and what's causing the issue for the indeterminate form. I'm going to keep the x minus 9 factored in the denominator because I now have the same factor in the numerator. So now we can say, wait a second, we've got common factors. Cancel them out. And remember, when you cancel it out, you're really just saying, I've got x minus 9 over itself, which is 1. So don't say, oh, this is 0 over the square root of x plus 3. That's not true. You still have a 1 in the numerator. But now we've rewritten this expression to an equivalent expression that clearly can't give us an indeterminate form. It can't because it doesn't have a 0 or even a variable in the numerator. So it's going to have a 1 in the numerator. Now we just have to focus on what happens in the denominator. So let's take the limit as x approaches 9 of our new expression, 1 over the square root of x plus 3. And we'll use direct substitution here. And we'll get 1 over 6 as the value of the limit. So very cool. The last thing I wanted to say about direct substitution was if you get, and I was trying to talk about this too soon a few minutes ago, but here we are at the special box. If you get some sort of a number that's not 0 divided by 0, this limit does not exist because there's a vertical asymptote there. The limit equals, let's see, what is my note trying to tell me? The limit equals, oh yes. The limit's going to either be infinity from one side or negative infinity from one side or vice versa. So the limit is either equal to plus or minus infinity. It could be infinity from one side, negative infinity from the other. we're going to look at an example of this case. So it's possible that the limit's infinity on both sides. It's possible the limit's negative infinity on both sides, or they could be heading in opposite directions. But something is happening at this asymptote where the function is just going to get increasingly large or increasingly small, and the limit is not going to exist. I mean, you have seen asymptotes before. You understand the behavior of a graph at an asymptote. The function that we're going to look at here, and let me change this to example 7 since we had that example 6 already. This is going to be the limit as x approaches -4 of 1 over x plus 4 quantity squared. Now, you're not going to get an indeterminate form here when you use direct substitution, but you will have an issue where clearly the function's not continuous at x equals 4. So we can use direct substitution, but it's not necessarily going to tell us what's happening to the graph. It's just going to tell us the limit does not exist. We need to figure out, though, what those limits are. So when you use direct substitution, -4 plus 4 is 0, and you end up with 1 over 0. Now, 1 over 0 just means the limit does not exist. The function's undefined. So we could say it's undefined. The limit does not exist. You need to figure out, though, well, what is the limit? So if I just said find the limit, I want you to tell me what the limit is. If it's infinity or negative infinity, don't just say like, doesn't exist, because in this case, there's a vertical asymptote. Like something is happening there. We need to figure out what it is that's happening. So we're going to plug this function into our y equals 1 divided by parentheses x plus 4 quantity squared. And you can create a table of values, or you can look at the graph and see what's happening at x equals -4. I'm just going to look at the graph. That's the fastest way to do this. Okay, so now you can see where you've got that vertical asymptote here at x equals -4. And as x approaches -4 from the left, the y values just go up without bound. So they're approaching positive infinity. As you approach -4 from the right, as x approaches -4 from the right, the y values again are increasing without bound. So you have this graph at -4. You've got this vertical asymptote, and you've got these two legs of your graph that approach the same value. And we would say that the limit of the function then would be infinity. So don't just say dne. I want you to tell me what the limit is. It's infinity. Now, if you had a different situation where you were approaching a different infinity from each side, like maybe one side was heading up and then the other side was heading down, that's a situation where you'd have to tell me the limit does not exist because they're approaching different values on each side. But in this case, they're both heading the same direction. You can tell me that the limit is infinity. This is another one you could have done with the table of values by just choosing values of x approaching -4. So maybe you would have said, okay, well, as I approach from the left, I'm approaching from like -4 point, I don't know, 0, 1, -4.001, -4.0001. See how large those y values get. And then as you're moving to the right of that, maybe you're at -3.9999, et cetera, 3.99, so on and so forth. So you don't have to do that for this one. I think I already maybe did this for you, but oh yeah, we can just look at it because we already have it in our calculators. Why not? The function's in there. Go to your table. If I put in something like -4.01, this value that I'm getting is 10,000. So that's huge. And then if I did -4.001, well, now I'm at 1e6. And if you're like, what's 1e6? Well, the e just means times 10 to the power 6. And that's a huge number. That's 1,000,000. So you can tell that these values are getting really, really large as I get even closer to 4. or to negative 4. Now we're at 1 times 10 to the 8th power. So these values are gigantic. And if you're looking at values, even just like 3 point, oh gosh, I have 4 9s in here. That gets me again to 1 times 10 to the 8th. So you can see that on both sides, we're just approaching these incredibly large values. Negative 3.99 gets us to 10,000. So these values get very, very large as you approach negative 4 from both sides. So that's how you can tell that that limit's going to be infinity. They're doing the same thing on both sides. So 2 different ways of looking at it. If you look at the graph, that's fine. On an exam, you can just say from calculator graph or just jot it down so I can see that you got that from somewhere. Okay. What else do we have to do here? We need to talk about limits approaching positive or negative infinity. I got to cut this off because I got to run and pick up the little one from preschool. So sorry, I'm going to splice these together and hopefully won't be too super awkward.